Welcome back to Quantum Computing in Practice. This is episode 6. Today we're going to focus on one of my favorite applications of quantum computers, simulating nature. In this episode, we are going to discuss the steps required to do this for any sort of quantum dynamics problem, which is the problem of finding how the description of a quantum system changes with time. We'll do this at a high level first, and then look into a specific example and walk through it in detail. Namely, the 2023 IBM experiment that demonstrated quantum utility. For some quick motivation at the start, one of the most famous stories that those of us in the field of quantum computing tell again and again, the story of Richard Feynman giving a lecture at Caltech in 1959 and basically providing motivation for the entire field for decades to come. The speech was called "There's Plenty of Room at the Bottom," a funny title, but the basic idea was that he was claiming there was still so much rich physics to be discovered at the microscopic level. Now, that specific talk wasn't given much heed until the 80s, when technology had developed quite a bit. And Feynman also clarified and refined his message over time. He returned to Caltech in the 80s and presented another paper called Simulating Nature with Computers, where he specifically said he wanted to talk about the possibility that there is to be an exact simulation that the computer will do exactly the same as nature. Essentially, being able to get rid of crude approximations of what goes on at the atomic scale and replace them with computers that understand and harness quantum physics, to not just simulate what nature is doing, but emulate it. Now, recall this timeline graphic I showed in a previous episode. At one end, we had problems that were easy to solve and will not require any sort of speed-up quantum could offer. But at the other end, we have problems that are very hard and need fault-tolerant quantum machines, which we don't yet have. Luckily, we believe that there are quite a few simulation problems that lie here in the middle, which is the region that we can currently work in. And there are lots of reasons to be excited and intrigued by this prospect, because the simulation of nature is the basis for a lot of exciting application areas. Just to name a few, if we could better simulate nature, we could accelerate the discovery of new materials, create better pharmaceuticals and medicine, or even explore new physics underlying particle physics or cosmology. But before you or I or anyone can attempt to apply quantum computing to these exciting areas, for now, they will need to understand the basic steps in a typical simulation-based workflow. First, you'll want to identify a quantum system of interest. This will inform you about the Hamiltonian governing its time evolution and a meaningful description of its starting properties, or its state. Then you'll need to find an appropriate method to implement the time evolution of this state. With these ingredients sorted out, the next steps involve carrying out the actual experiment. These generally involve optimizing the quantum circuit implementation of the time evolution algorithm, executing the circuit or circuits on quantum hardware, and post-processing the results. So we can name the basic steps involved in a simulation experiment as follows. Identifying the system Hamiltonian, Hamiltonian encoding, state preparation, state evolution, circuit optimization, circuit execution, and post-processing. But these are quite detailed steps. Remember that the 4 stages of the Qiskit patterns framework, which helps us understand how to implement a routine in Qiskit, are mapping, circuit optimization, circuit execution, and post-processing. So these 4 first steps here are actually all included under the umbrella of mapping. And that's why we spent an entire episode on this first stage. And if you missed that, please go back and watch the previous episode. Now let's first walk through what these steps even mean before we dive into any coding. So the first basic thing we need to do to perform a simulation experiment is to identify the Hamiltonian that describes the system. Sometimes, often, these are well known. Other times, we have to put it together from understanding the energy contributions of the small subsets of the full system, like so. where HI is the Hamiltonian acting on one of the n local subsystems of H. We will also need to note if the system consists of fermions or bosons, if we are dealing with elementary particles. Next, we need to encode the Hamiltonian and translate it into terms quantum computers can understand. Oftentimes, these Hamiltonians will be made up of elementary particles or spin systems. If we were simulating fermions or bosons, we will need to choose an encoding transformation like the Jordan-Wigner or Bravais-Kitev. These transformations will tell us how to translate the definition of the Hamiltonian written in terms of the original components, the fermions or bosons, into Pauli operators, which are easily converted into gates on a quantum computer. For example, the Jordan-Wigner transformation defined here gives a mapping from fermion operators to Pauli operators. If we are already dealing with spin 1/2 systems, which are very common, then we're good to go, aside from any possible normalization coefficients, and we don't need to use an encoding scheme. Having encoded the desired Hamiltonian into the quantum computer's gate set, the next crucial step is to determine the appropriate initial quantum state from which to begin our simulation. This state should ideally reflect some physical meaning or configuration of the system under study. For example, if we're interested in exploring the ground state energy of a molecule, we might start with a Hartree-Fock approximation, or another easily preparable ansatz that has significant overlap with the true ground state. The choice of initial ground state affects not only the convergence of variational algorithms like VQE, the variational quantum eigensolver, but also the accuracy and efficiency of time evolution or sampling in the quantum phase estimation. In essence, the initial state serves as the launching point for the computation, setting the stage for extracting useful observables about the quantum system that we're modeling. The preparation of an arbitrary n-qubit state, where Ci are the computational basis states, and Ai is each state's respective coefficient, and the normalization condition 2n-1 can generally be approached by initializing the state with the operator O. The starting state would be the all-zero standard basis state, often written like this for simplification. In general, this requires an exponential number of C0 gates. Oftentimes, we are interested in a specific initial state for the system, and its preparation can be implemented with a reasonable amount of resources. Product states, for example, in which the qubits are not entangled with each other, only require single qubit operations. Now, we haven't actually had the opportunity to talk about trotterization yet, though some of you are probably already familiar with it. In essence, trotterization is a method for calculating matrix exponentiation that uses approximations to handle the exponential nature of non-commutative operators. When two operators, like HA and HB, don't commute, then we must apply a clever trick and alternatively apply the corresponding exponentials of e to the minus I HA and e to the minus I HB. For n number of times the alternating evolution operators are applied. I won't go over the proof here, but I will share a link to a nice simple proof of this statement in the description. But the take-home message is this. Time evolution is an important part of mapping too. Trotterization breaks up a continuous interaction into discrete steps that can be implemented on a quantum computer. After generating the trotterized circuit, we have finally finished the mapping step. We can now move on to circuit optimization. To do that, this is what needs to be accomplished. There needs to be a qubit layout that maps the virtual qubits of your circuit to physical ones on the hardware. This is needed because hardware can have particular topologies which restrict the direct interaction of physical qubits, while implementation of a quantum circuit often assumes the ability for any qubit to interact with any other qubit. Then, we need to insert swap gates as needed to route interactions between qubits that are not connected. We need to translate the gates in our circuit to instruction set architecture, or ISA instructions, that can directly be executed on the hardware. Then we need to perform circuit optimizations to minimize the circuit depth and gate count. This step can also be performed on the virtual circuit, the circuit where the qubits have not yet been mapped to a device topology yet. But remember, much of this is done automatically for you in Qiskit. We will see exactly how in the next section of this lecture. After the optimization step, we are ready to run the circuit using a primitive. For most simulation experiments, you are interested in understanding the change of certain properties of the system with time. So it's likely you will be using the estimator primitive, because that will let you measure the expectation values of observables corresponding to specific properties. Then we will configure the best options for the estimator, which can add error suppression and error mitigation techniques. Finally, we will run the experiment. The last step is to post-process all the data. This extracts the measured expectation values, or if you're using the sampler, the sampled probability distribution in the computational basis. If all one needs are the expectation values of the observables of interest, these can be directly obtained from the estimator primitive, both in their raw and error-mitigated values. Oftentimes, one will then use the measured expectation values for other calculations for other quantities of interest, which don't require quantum computation and can be computed on a classical computer. Now, we are going to walk through a real example from a very influential paper IBM published a couple years ago, called The Evidence for Utility of Quantum Computing Before Fault Tolerance. Now, this paper, which we abbreviate fondly as the utility paper, became a very influential paper in the field of quantum computing almost immediately upon publication. The overall thesis of the paper is that a noisy quantum computer produced accurate results, or expectation values, using 127 qubits and 2,880 gates, outside the capabilities of brute force computation, which is the exact simulation of the quantum circuits executed by the hardware. This work was also important because it showed that a quantum computer could be used to verify or compare results with other approximate classical methods for quantum simulations, such as tensor network algorithms, where the solution was not known a priori. What is also rather cool is that now others, using the IBM quantum systems on the cloud and Qiskit, can duplicate and verify these results themselves. I'm going to walk you through how to do just that. So for this example, we will get a little bit more specific about the steps involved in mapping this problem into inputs that can be understood by a quantum device. In this case, we will be simulating the dynamics of the total magnetization of a system of magnetic dipole spins on a lattice in the presence of an external magnetic field. The system can be described by an Ising model with a transverse magnetic field. We model this with a parameterized quantum circuit, where the parameters correspond to the tunable value of the spin-spin, or ZZ, interaction, and the strength of the magnetic field, X. Now, this series is called Quantum Computing in Practice. So we're also going to discuss procedures in this experiment that we're going to implement to make the results as good as possible. So next, we are going to discuss how to remove bad qubits, or qubits with low gate fidelities or decoherence times, which could drastically affect the experimental outcomes. These bad qubits can occur due to poor prior calibration or two-level systems interacting with the qubit. Removing some qubits from the hardware native topology corresponds to considering a system on a lattice described by the resulting topology. We are also going to discuss creating the parameterized quantum circuit, which implements the time evolution of the system via trotterization. For this purpose, it will be important to identify entangling layers, which are a critical part for the main error mitigation technique we are going to use later on. So at this point, I want to make sure that you, the audience, know that you can follow along with everything that I'm about to discuss in the tutorial linked below and on the IBM Quantum Learning platform. In this tutorial, what you might notice is that we have created a series of helper functions early in the notebook that we can call upon later to make our lives a little easier. I want to mention these now, not because it's part of the official or formal process, but because this is often what experimentalists do in real life to help them run these types of experiments. And it also shows us how we are going to break down our problem even further. The functions we define in the notebook are as follows: remove qubit couplings, define qubit couplings, construct the layer couplings, construct entangling layers, and lastly, define trotterized circuit. Next, let's talk about layer couplings, which help define how qubits interact with their neighbors during the simulation. Our quantum devices use something called the heavy hexagonal layout, a special pattern for connecting qubits. In this layout, we can group the connections, called edges, into 3 separate sets, where no 2 connections in the same set share a qubit. This is important because on a real quantum computer, we can't run 2 qubit gates at the same time if they involve the same qubit. Each qubit can only be involved in 1 gate at a time. By dividing all the connections into 3 layers, we can apply 2 qubit gates across the entire device in 3 rounds, making sure no qubit is used in more than 1 gate per layer. These gates implement the ZZ interaction from the Ising model, and they're repeated at each step of the simulation, called the trotter step. Twirling modifies the noise in the device so that even a simple noise model is likely to be accurate. This also makes it possible to accurately learn the noise model and use the obtained information in error mitigation techniques. Next, we have to remove our bad qubits from our possible list of physical qubits that we can use for the experiment. Like I said, a qubit can become bad for a variety of different reasons. Sometimes it's just a bad calibration, a simple mistake that can be resolved by just calibrating again. Sometimes it's a bit more complicated and related to something that we call a TLS, which is a 2-level interfacial defect that leads to qubit parameter fluctuations and relaxation. This can be resolved by warming up the whole system a bit and then cooling it back down. But that takes a while and isn't possible to do over the cloud. So for now, the easiest thing to do is just exclude them from our list of possible physical qubits that we'll use. You can identify which qubits are not behaving expected easily from the IBM Quantum platform. You can plot the qubit characteristics there in the platform or download them as a CSV. Then create a list of all the qubits that you want to exclude and simply remove them from the list of total physical qubits on the device. All right, now let's continue on with our mapping step, generating our trotterized circuit. Now, as we showed earlier, trotterization discretizes the time evolution into a series of steps, and we need to decide how many steps. We'll choose 6 here. But in general, the strategy is to balance something called the trotter error, which is an algorithmic approximation error, with the error arising from decoherence. More trotter steps reduces the approximation error, but require deeper quantum circuits, which experience more decoherence noise. We will define the circuit in terms of the theta parameter, which is the strength of the external magnetic field, layer couplings, and the number of steps and qubits, and of course, the device backend. Because of the dependence of the magnetization of the system on the strength of the external magnetic field, it is interesting to execute the simulation at various values of the magnetic field strength, which translate into different angles of Rx on the rotation for Rx in the circuit. Now, with having generated our circuit, we'll move on to its optimization. First step here is to define a paths manager. Remember, in the context of the Qiskit SDK, transpilation refers to the process of transforming an input circuit into a form that is suitable for execution on a quantum device. Transpilation typically occurs in a sequence of steps called transpiler passes. A pass manager is an object that stores a list of transpiler passes and can execute them on a circuit. Create a pass manager by initializing a pass manager object with a list of transpiler passes. In the end, our pass manager will create an ISA circuit. a circuit that must be written in terms of the back-end's instruction set architecture, which describe the circuit in gates which are native to the back-end, but lack the timing information needed to run the circuit. Now we are ready to execute our circuit, which is step 3 of Qiskit patterns. Now, as stated before, we will definitely be using the estimator here as our primitive of choice for this experiment, since we want to measure the total magnetization of the system, and estimating the expectation value of the observables is what the estimator was designed for. In this step, it will also be crucial to specify our options for error mitigation. We will use zero-noise extrapolation to get the best results possible. Particularly in the tutorial, you will see that we specify 2 or more noise factor values at which to evaluate the extrapolated models and specify probabilistic error amplification as our amplification option. Now, probabilistic error amplification, or PEA, was really the error mitigation technique method of choice here because it scales so much better than the other options. And that's what's important when we're working at the level of 100 plus qubits. Last but not least, run the experiment, and it will take some time to complete. But for now, let's reference the data queued and stored from the tutorial. We will examine the metadata, making particular note of the layered gates and the mitigated layers, since we are about to use those to remove a bunch of errors from our raw data. We are almost ready to plot our final results. But before we do that, let's quickly add an interlude here on what exactly is meant by zero-noise extrapolation, or ZNE. We've covered it briefly in earlier episodes, but to review, zero-noise extrapolation is an error mitigation technique that removes the effects of an unknown noise during circuit execution that can be scaled in a known way. It assumes expectation values scale with the noise by a known function, shown here, where the lambda parameters specify the noise strength and can be amplified. We can implement ZNE with the following steps. First, amplify circuit noise for several noise factors, lambda 1, lambda 2, lambda 3, and so on. Run every noise amplified circuit to measure the expectation value A of lambda 1, A of lambda 2, and so on. And then extrapolate back to the zero noise limit, the expectation value A of 0. The main challenge in successfully implementing ZNE is to have an accurate model for noise in the expectation value and to amplify the noise in a known way. There are 3 common ways error amplification is implemented for ZNE. Scale pulse duration via calibration, repeat gates in identity cycles, and adding noise via sampling Pauli channels. We call the latter PEA. Probabilistic error amplification is the best choice here because pulse stretching is very computationally costly. Gate folding lacks theoretical guarantees in preserving noise bias, but PEA can be applied to any circuit that can be run with native noise factors but require learning the noise model. PEA assumes that the same layer-based noise model as probabilistic error cancellation. However, it avoids the sampling overhead that scales exponentially with the circuit noise. To learn the noise model, we must first identify the unique layers of 2-qubit operations in the circuit. For each layer, Pauli twirl the 2-qubit gates to ensure that the noise is well described by a damping noise model. Repeat identity pairs of layers at varying depth, and finally, bit of fidelity, or an error for each noise channel. And of course, while I recommend understanding this method to some extent, doing it by hand in Qiskit is much more simple, as is shown in the tutorial. Now finally, let's take a look at the plotted data. The dotted gray line shows the exact results obtained with approximate classical methods, with approximation error converged to a low threshold. As you can see, the raw data for the different factors of noise we chose at the beginning is a good ways away from this dotted line. The solid blue line shows the data taking into account our ZNE processing, and you can tell right away it's much closer to the exact results. In summary, the noisy values show high deviation from the exact values. The mitigated values are close to the exact values, demonstrating the utility of the PEA-based mitigation technique. And that essentially concludes this episode. To quickly summarize what we have learned, quantum simulation is one of the most promising application areas in the short to mid-term. It has wide-ranging applications, from pharmaceuticals to high-energy physics, material science, and more. The utility paper from IBM, published in 2023, pointed the way towards being able to use quantum computers for scientific discovery. And we worked through the associated tutorial that goes along with that paper in depth. The steps to work through a simulation problem, from start to finish, are relatively straightforward, especially once you get the hang of it. And my hope is that you can, from now on, use this video and the tutorial as a guide for even more simulation problems in the future. Thanks for watching, and we'll see you next time on Quantum Computing in Practice.